In this video, we are going to talk about CI/CD. Let's take a moment to recap one of the most important principles in DevOps. Everything that can be should be automated. The idea here is pretty simple. If there is a task that gets repeated often, like integration code, deploying updates, or delivering new features, we don't want people doing that by hand every time. That's slow, error prone, and honestly, it's just not scalable. When we bring in automation, we are not only saving time and cutting costs, but we are also making those processes much more dependable. You run the same scripts and you get the same results, no surprises, no inconsistencies between environments. And the best part, all that automation lives in scripts that are stored right in the project repository. Just like your source code, those scripts can be reviewed by team, tracked with version control, and improved over time. It's a cleaner, uh, smarter way to work, and it's a big reason why DevOps has become such a powerful model in software development. Recap DevOps principle, everything that can be should be automated. Let's break this down by looking at 4 key concepts that really define how DevOps streamlines software delivery. First, we have continuous integration. This means that every time a developer commits a change, especially to the master branch, the system automatically kicks off a build. That includes compiling the code, running automated tests, generating artifacts, and making sure everything integrates correctly. The goal is to catch problems early before they grow. Then comes continuous delivery. Here, the software that passed integration is pushed to a staging or pre-production environment. This is where the QA team gets involved. They run more thorough tests in an environment that mirrors production, so we can confidently say the software is ready to go live. If we take it one step further, we reach continuous deployment. This is when every successful change that passes testing is automatically released to users. There is no waiting for a manual deployment or a scheduled release. It just goes live. This model is fast and efficient, but it depends on having strong testing and rollback system in place. And finally, we have infrastructure as code. Instead of manually setting up servers, networks, or installing tools, everything is done through scripts. These scripts can configure environments, install dependencies, and set up your infrastructure just like any other piece of code, making it repeatable, version controlled, and scalable. Now let's talk about system integration. This is where everything comes together to form a working system. Think of it as assembling all the puzzle pieces, code, databases, configurations, and external services into one complete functioning product. The process usually starts by setting up your database. That means installing the necessary software, defining the schema, and loading in some test data so the system has something to work with. Next, we compile the source code. Once the code is built, it's linked with any required libraries or dependencies. This ensures all the pieces talk to each other correctly. Then we check that any external services like APIs or authentication systems, so they are up and running. These are often easy to overlook, but they are critical for the system to operate. We also clean up outdated configuration files and move current ones into the proper locations. That's key for making sure the environment behaves as expected. And finally, we run system tests. These aren't just unit tests, they are broader checks that verify whether the entire system as a whole is functioning properly. There are tools to help managing this process. For example, Make, Ant, Maven, and YAML scripts can automate much of this work, so it's consistent and repeatable across environment. Let's talk about continuous integration or CI and why it is such a powerful part of modern software development. The core idea is simple. Every time a developer pushes a change to the repository, the system automatically builds and tests the updated version of the software. So instead of waiting until the end of the week or worse, the end of the month to find out if something broke, we find out within minutes. What actually happens behind the scenes is that once the push is complete, the repository sends a signal to the integration server. That server then builds a new version of the product and runs a set of automated tests on it. And here is the real benefit. When a test fails, you know exactly where to look. If only one or two new changes were pushed, then the problem is almost certainly in that new code. It saves tons of time compared to trying to untangle bugs in a large delayed merge. Continuous integration is like a safety net. It helps teams catch mistakes early and fix them before they spiral into bigger issues. This diagram gives us a high-level view of the continuous integration pipeline. Essentially, the steps a system goes through from the time new code is pushed to the point it becomes a deployable product. We start with the get step. This is where the system automatically retrieves the latest source code from the repository. Think of this as checking out the newest version of the code every time someone commits a change. Next, we move to compile and build. Here, the system takes that source code along with any required libraries, configuration files, and possibly even test data and compiles it into executable system. So this is the point where we go from human readable code to something that the machine can actually run. Once we have a working executable, we move to the test phase. Automated tests are run, usually unit tests, integration tests, and maybe some smoke tests, just to make sure everything is functioning as expected. And if all tests pass, we now have a deployable system. This means the system is packaged and ready to go into staging or production. It's not just theoretical code anymore. It's something you can actually deliver. This whole flow is typically triggered automatically whenever changes are made, which keeps integration fast, consistent, and reliable. This slide talks about a common issue in continuous integration called breaking the build. What that means is when a developer pushes their code to the repository, it triggers the integration process. And if that new code causes any of the automated system tests or fail, the build is considered broken. It's like putting a faulty part into an assembly line and having the not work. In a CI environment, it's really important that we avoid breaking the build. A broken build can block other developers, slow down the team, and create confusion about what version of code is stable. So how do we prevent this? One helpful strategy is to follow the integrate twice approach. What that means is before pushing your changes to the central repository, you first pull the latest version of the code, merge it with your local changes, and run all the tests on your own machine. If everything passes locally, then you go ahead and push it. This way, you catch any potential issues early and avoid disrupting the rest of the team. To make continuous integration work well, speed is key. Developers need to get feedback quickly. If they are waiting too long for builds and tests to complete, it defeats the purpose. But the reality is that some parts of the build process, like compiling a large code base or initializing a database, just take time. So to keep the integration process efficient, we rely on an automated build system that minimizes delay wherever possible. One of the best ways to do this is through incremental builds. And instead of rebuilding um, everything from scratch, we only rebuild the parts of the system that were actually changed. That way, developers get faster results and can iterate more quickly without sacrificing reliability. All right, so what we are looking at here are two dependency diagrams that help explain how build systems decide what needs to be rebuilt and when. In figure 1, we are working at a higher level. Think of this as a big picture for running system tests. To run those tests, we need two things, the executable system itself and the test scripts. So those arrows pointing up indicate that both of these inputs are required before the task can happen. Then in figure 2, we zoom into a lower level. Here we see a dependency graph for creating object code from a specific source file. In this case, something like mycode.cpp. We see that creating the object file depends on the source code itself and any related configuration or header files. If any of those change, the build system knows it needs to recompile that file. This slide is explaining how an automated build system knows when to rebuild code. It does this by checking timestamps, specifically the last time a file was modified. Let's say you have a source file and a corresponding compiled file. If the compiled file is newer than the source file, that means no changes were made to the source after compilation. So no rebuild is needed. But if the source file is newer, so you edited the code, the system knows it has to recompile. Now there is a third case. Even if your source code hasn't changed, it might depend on an external file or library, like a class definition. If that file has changed and is newer than your source file, your source has to be recompiled anyway to stay in sync. This slide walks us through the difference between continuous delivery and continuous deployment. In continuous delivery, we automated everything up to the point of deployment. So every time a change is made and pushed to the repository, it goes through integration and testing, and we package it as a ready-to-deploy version. But we don't actually deploy it yet. There is still a manual decision involved. Why? Because we recognize that the production environment might differ from development or test environments, and that can introduce new bugs or unexpected behavior. Now, continuous deployment takes it a step further. Here, once the change passes all tests and get packaged, it's automatically released to users. There is no human gatekeeper. But to safely do that, we have to make sure we have tested it in a real or production-like environment. So that things like hardware, network differences, or external APIs don't break the deployment. This diagram nicely breaks down the two stages, continuous delivery and continuous deployment. So let's look at the top half first. This is continuous delivery. It starts by configuring a test server to simulate a real environment. Then we install the software on that server and run a suite of acceptance tests. These tests help us verify that the system behaves as expected from the user's perspective. Once all tests pass, we have a fully validated and tested system that's ready to go, but deployment hasn't happened yet. This stage ends with software that's ready for production but requires a manual green light to move forward. Now moving to the bottom half, if we decide to automate the next step to actually installing the software on production servers and switching users to the new version, we move into a continuous deployment. That means no manual gatekeeping. Even approved change goes live automatically. This slide highlights several key benefits of continuous delivery. First, cost. Yes, setting up an automated deployment pipeline is initially expensive. It takes time and resources, but the payoff comes quickly if you are making frequent updates. Manual deployment simply doesn't scale. It's slow, prone to human error, and ends up costing more in the long run. Now, faster problem solving is another big advantage. When you are deploying in a small incremental updates, if something goes wrong, the scope is small. You know exactly what change triggered it, and it's easier to isolate and fix. Compare that to a large bundled release. If something breaks there, you have to dig through a ton of changes to locate the issue. And finally, faster customer feedback. With more frequent updates, you are not waiting months to learn whether a feature works well for users. You can release quickly, collect feedback quickly, and improve quickly. And if you're working at a scale, you can even run A/B tests by serving different versions of the system to different groups of users, thanks to load balancers. That way, you can make data-driven decisions before rolling out to change to everyone. All right, let's talk about something that's become a game changer in managing enterprise systems, infrastructure as code. So imagine an enterprise setup. You have got all these different servers. Some are web servers, some are database servers, others might be file servers, and each of them has its own setup, different operating systems, different configurations, or different software packaging running. Now try keeping track of all of that manually. It gets messy really fast. That's where infrastructure as code comes in. Instead of logging into each server and installing things by hand, we write scripts just like code that describe what each machine should look like and what it should run. This makes the whole setup process repeatable and consistent. And tools like Puppet and Chef help with that. You just define your infrastructure, and these tools take care of setting up everything automatically, installing the right software, configuring services, and so on. The big win here is twofold. First, it lowers the cost of managing all these systems, and second, it reduces the risk of those "it worked on my machine" kinds of problem, because now every server is set up exactly the same way every time. This diagram gives us a visual understanding of how infrastructure as code actually works in practice. So over on the left, we have something called the infrastructure definition. Think of this as a blueprint. It's a script or configuration file where we specify what each server, for example, S1, S2, S3, or S4, needs. So for example, maybe S1 needs a web server and a firewall, while S3 and S4 need the same database setup. Now, instead of logging into each server and doing these installations manually, we pass this blueprint into a configuration management tool, CM tool, something like Puppet, Chef, or Ansible. And CM tool reads through the definition and knows exactly what to install, where to install it, and how to configure it. From there, it pushes out the required software to the appropriate servers, S1 through S4 in this diagram. Everything gets set up automatically and consistently based on the definition we have provided. So really, this is about removing manual work, reducing human error, and making infrastructure setup predictable and repeatable. Now let's walk through some of the key benefits of using infrastructure as code and why it's become such a best practice in DevOps. First of all, visibility. When your infrastructure is defined in code like a model, it's no longer stuck in someone's head or hidden away in random scripts. It's clear, shareable, and version controlled. That means everyone on the DevOps team can read it, talk about it, understand it, and give feedback. It's transparent, just like good software design. Next, we have reproducibility. This is huge. Once you define your setup and use a configuration management tool to apply it, the same steps run in the same order every single time. So whether you are spinning up one server or 10, you get the exact same environment. No surprises, no missed steps. You are not relying on someone to remember the right way to set things up. Then there is reliability. Let's be honest, even experienced system admins make mistakes, especially when repeating the same change across multiple machines. But when you automate the process, those little manual errors disappear. The tool doesn't forget and it doesn't get tired. And finally, recovery, since your infrastructure is code, you can treat it just like application code. Version it, store it in Git, and roll it back if needed. So if a new configuration breaks something, no problem. You just revert to an earlier version that you know was working and just apply it. This kind of control and consistency is exactly what makes infrastructure as code so powerful in modern software delivery. Let's shift gears and talk about containers, especially in the context of tools like Docker. A container is especially a self-contained execution environment. It runs on top of an operating system, usually Linux, but it behaves as if it's isolated. That means it comes packaged with everything it needs to run: code, runtime, system tools, libraries, everything. Now, the way we define what goes into a container is through a Docker file. Think of a Docker file as your receipt. It lists all the software dependencies and configurations needed. So again, we are seeing the theme of infrastructure as a code. You are not clicking around setting things up, you are writing down exactly what the environment should look like. When we process that Docker file, Docker builds an image, which is an executable snapshot of the environment. And because you can rebuild that image anytime, you can perfect reproducibility. Whether it is on your laptop or in the cloud, the container behaves the same. What's powerful here is that you can build different images for different types of servers. So your web server, database server, and analytics server could all have their own tailored environment. And here is something especially useful. There is no distinction between deployment testing, development testing, or production environments. The same container image can be used across all stages. You want to test a new version? Build a new image, spin it up, next to your running system and gradually start sending traffic to it. If anything goes wrong, it's easy to roll back, just switch traffic back to the previous image. This flexibility and consistency is why containers have become such a core part of modern software deployment. Let's take a step back and look at the bigger picture. Literally, on the left, you see how shipping used to work. Tons of workers manually loading and unloading individual items. It was chaotic, so slow and incredibly inefficient. Each shipment was unique, which meant different handling and packaging every time. Now, fast forward to the image on the right. What changed? Standardized containers. This shift revolutionized global trade. Today, 90% of all cargo is shipped using these uniform containers. Why does it matter? Because it allows for automation, planning, and speed. There has been an order of magnitude reduction in both the cost and time it takes to load and unload ships. It also drastically cut down on losses. When you are dealing with individual items, it's easy for things to get stolen or damaged. But when everything is sealed in a container, those risks drop dramatically. Then look at freight costs. They used to make it up to over 25% of a product's final price. Now it's often less than 3%. That reduction is what helped drive massive globalization. Companies could manufacture goods halfway around the world and still sell them competitively. And just to give you a sense of scale, there are about 5,000 ships more moving 200 million containers every year. Why are we talking about this in a software or DevOps class? Because the same principles apply to software containers: standardization, automation, efficiency, and scalability. We will see more of that in just a moment. All right, now let's break down the different types of container technologies, because not all containers are built the same way or serve the same purpose. Let's start with the most common one, the application container. This is what Docker, Podman, and Singularity are all about. These containers are designed to run a single application or server. So think of them as lightweight, focused, and portable. You package the application along with its configs, libraries, and dependencies, and that is it. It's perfect for microservices and single-purpose tools. Now compare that to a system container like LXC or OpenBees. Uh, this was developed by retrozoom. System containers go a step further. Instead of just packaging one application, they provide a full operating system environment. That means you can run multiple processes or services within the same container, almost like having a lightweight VM. The diagram on the left helps visualize this. With the application container, you see just one main service. With system containers, we have got multiple services bundled together, maybe a main service surrounded by supporting ones like schedulers, daemons, and logging tools. Then on the top right, we compare these container technologies to virtual machines. VMs are heavier. They run a full guest OS on top of a hypervisor. That makes them more resource intensive, but also more isolated. So to summary, application containers like Docker are fast, lightweight, and great for isolated services. System containers offer more of a full system experience with multiple services, and VMs give you complete operating system level separation but at a higher source cost. Each has its place, and depending on your use case, whether you are running a single microservice or a full service stack, you will pick the right one accordingly. Okay, so now let's take a closer look at how Docker containers are actually built and run, and where Docker Hub fits into all this. We will start at the bottom left corner with the Docker file. This is your blueprint. It's a plain text file that includes instructions like from, at, run, and cmd. These commands tell Docker what base image to start from, what files to copy in, what commands to run, and how to start the application. That Docker file is combined with a base image file, usually pulled from Docker Hub, which is basically a public registry of pre-built images. Think of it like GitHub, but for Docker images. You can grab existing images for things like Ubuntu, Python, MySQL, and so on. Then, using the command docker build, Docker processes the Docker file together with the base image and produces a new image file. This image is now a portable, complete environment that includes your app and everything it needs to run. Now, here is the final step. We use Docker run on that image file to launching a running container. This is where your application is live and executing, completely isolated from the host system, but fully functional. So to recap, first write a Docker file to define your environment. Second, use Docker build to create a custom image. And third, use Docker run to start the container. And that's the full cycle from definition to deployment in just a few steps. So as you adopt DevOps practices, one thing to always keep in mind is that it's an ongoing process. You are never done. The goal is to continuously improve, to deploy faster with better quality and more confident. Now, to actually know if you are improving, you need to measure, and not just one thing, but multiple dimensions of your software and your process. There are four main types of measurement we care about. One is the process measurement. This is about how you build and deliver your software. How long do builds take? How frequently are you deploying? Are you test passing consistently? This helps you identify bottlenecks in your development or CI/CD pipeline. Second type of the measurement is service measurement. Now we are talking about the software in action. Is it reliable? Is it performing well under load? Are users experiencing downtime or latency? This helps you assess the quality of the deployed service. Third is usage measurement. Here you are tracking how people are actually interacting with your application, which features are used the most, where do users drop off. This is key for prioritizing development. It helps you focus on what users truly care about. And the last one is business success measurement. We tie it all back to the big picture. Is the product helping the business succeed? That could mean increased revenue, more customers, lower churn, and hitting strategy goals. It's the highest level of measurement and arguably the most important in the long run. So when we say measure DevOps success, we are not just looking at build time or uptime. We are talking about comprehensive view across process, product, users, and the business. To effectively improve anything, you have to measure it. And the same goes for software systems. One of the best things you can do is instrument your software to collect data about itself. This means building in hooks or logging so the system can report on things like request times, error rates, or resource usage. The idea is to give the software the ability to reflect back useful information. So we are not just guessing about what's happening. In addition to instrumentation, we also rely heavily on monitoring tools. Tools like Prometheus, Datadog can collect and analyze all that data in real time. They let us track key metrics like uptime, CPU usage, memory consumption, and service latency. This is what helps operations teams detect problems early and respond before users are impacted. Now, some of your process measurements, like how long a build takes or how many deployments happen per day, can also be automated. Those are easy to track using CI/CD tools, but it's not always straightforward. When people are part of the process, like developers, testers, or reviewers, things get a little messy. Everyone works differently, and not everyone records information the same way. Plus, human performance isn't consistent. It can be vary day by day. So the key takeaway here is automate and instrument whether you can, but also recognize where their limits are. It's okay that some parts of your process are harder to measure. The goal is just to gather enough data to make smart, informed improvements over time. All right, this starburst diagram gives us a great snapshot of the kind of DevOps metrics we want to track and how they fall into two big categories, process metrics and service metrics. Let's start at the top with process metrics. These help us understand how efficiently and effectively our development and delivery pipeline is running. Deployment frequency means how often are we releasing code and the high performing DevOps teams aim to deploy multiple times per day. Change volume, how big or complex are these changes? Smaller incremental updates tend to be safer and easier to manage. Lead team from development to deployment. Once a change is committed, how long does it take to get it into production? Percentage of failed deployments. This tells us about quickly and quality and risk. Are our deployments stable or causing rollbacks? Mean time to recovery. When something goes wrong, how quickly can we detect it and fix it? Now, on the bottom half of the diagram, we are got service metrics, which tell us how the system performs in the real world from the user's perspective. So we have performance, which is are things fast and responsive? Availability, is the system up and running when users need it? Number of customers complaints, which says what are people actually saying about the product? And percentage increase in customer numbers, which is are we gaining traction? This ties DevOps performance directly to business growth. Together, these metrics give us a holistic picture. We are not just focused on how fast we deploy, but also on how those changes impact user experience and business outcomes. So, in a healthy DevOps practice, you want to track a balance of these metrics because deployment fast doesn't matter if your service is slow, buggy, or unavailable to customers. This slide brings everything we have discussed about DevOps metrics into a more practical, actionable framework. This approach was proposed by Payal Chakravarty from IBM, and it's built around a metrics scorecard. Essentially, a focused set of 9 key metrics that you can actually track and improve on. This is especially relevant for software delivered as a cloud service, where feedback loops are fast and data is plentiful. Let's break it down into two groups: process metrics and service metrics. For the process metrics, there are three things we want to reduce: failed deployments, so obviously fewer is better; mean time to recovery, so how quickly we bounce back from failures; and lead time from development to deployment. The shorter, the more agile and responsive we are. And two things we want to increase: deployment frequency, which is how often we are shipping to production, and change volume, measured here in terms of how much code is getting delivered. The assumption is that healthy delivery teams are pushing out useful changes regularly. Now for the service metrics, this focuses on what the end users experience. Availability and performance should ideally be stable or improving. That's your baseline quality. The number of customer complaints should be dropping, a clear sign that things are working well. And ideally, the number of new customers should be rising, showing that your improvements are helping the product grow. So this 9 metric scorecard gives you a balanced, real-world way to monitor your DevOps health. You are not just measuring speed, you are also watching quality, customer satisfaction, and business growth. That's what makes it so powerful. Now let's talk about what it actually looks like to track DevOps metrics over time. This chart shows three metrics we have been discussing: availability, deployment frequency, number of customer complaints. And along the bottom, we are tracking them week by week. So this is what we would be monitoring in a real world DevOps environment. You might use a chart like this to identify trends or correlations. For example, if deployment frequently increases in week 3, what happens to availability? Or do customer complaints go down as uptime stabilizes? Maybe in week 4, you notice a dip in availability and a spike in complaints. That could indicate a bad release or infrastructure issue. By tracking these side by side, you can start connecting the dots and asking the right questions. Charts like these are really helpful not just for engineers but for product managers and leadership too. They allow everyone to visually track the health and progress of the system and align efforts around both technical quality and user satisfaction. This diagram gives us a simplified view of how logging and monitoring work in a DevOps environment and how we go from raw activity in the system to meaningful metrics. So over on the left, we start with the executing software. This could be your web app, API service, background job, and etc. As it runs, it generates logs. These logs record things like requests, responses, errors, resource usages, and timestamps. Basically, a record of what's happening under the hood. Each component might have its own log. So here we see log 1, log 2, and log 3 representing different sources or services. These logs then get passed to a log analyzer, which could be a tool like ELK Stack or Splunk. This tool parses the logs, extracts useful information, and often stores it in a more structured form. For example, how many requests failed, or what was the average response time. Finally, the processed data is visualized in a metric dashboard. This is what teams look at day to day. Tools like Grafana, Kibana, or Datadog let you build dashboards that show live metrics so you can see how the system is performing in real time and catch issues before they become critical. So really, the point here is that logs are much more than just error messages. They are the raw material we use to build visibility into our system. Okay, so we're done with this, with the section CI/CD, and thank you for watching this video.